Last time we talked about this little robot loop. It sends actions to an environment, and we get a world state back. And there's some algorithms in this robot's head that we're going to learn how to develop. And this robot also has a model of the world in its head in some cases. And the question is, well, how do we model the environment? Like if we're going to develop algorithms that solve problems, we need some formal way of modeling the world and the environment. And it's going to be through some sort of probabilistic state transition system. And we're going to call this a Markov decision process. These are very well-known and well-studied models. And we gave this example of solitaire. We don't need to go through that again. But it's going to be very useful to have a notation, a graphical notation for writing down Markov decision processes that we can sort of look at really tiny examples and gain some intuition. And so I'm going to go through what that graphical notation looks like. And this is pretty typical. I mean, people will use squares and circles in different ways. But the first thing that you need to specify in a Markov decision process is the state space. This is what states are there in the world. And in our world, there's an enormous number of states. Like you wouldn't be able to draw a circle for every one of them. In this world here, we're just going to have two states. So you might think of it as there's a thermostat that we're controlling, and there's just two states. It's warm enough or not warm enough, right? It's kind of a silly example, but it's a binary world with just two states. So those are the states. The world can be in any of those states. And what makes this more interesting is when you add actions to the equation. So typically we're going to describe actions in this graphical notation by having these lines drawn to boxes. So in this case, there's two actions in every state, A0 and A1. And what this means is that when we're in state 0, or our agent is in state 0, it has a choice between these two options. Okay? And maybe if this is a thermostat, it can turn up the heat or turn down the heat. Right? That would be an example of two types of actions. Now, this doesn't tell us too much, right? It doesn't tell us what the actions do. So we need a notation to say, what do the actions do? If I take action A0 and S0, what happens? And we're going to show that partially by drawing these arcs. This shows that in S0, if you take the action A0, there's two possibilities that could happen. You could either go to S1 or S0. Or if you take A1, there's only one possibility. You can only go back to S0. That's kind of like a no-op action, right? You just stay where you are. Now, what's missing here, would you say? Probability, right? So now there is a whole class of planning and control problems where you sort of stop at this point. You just talk about, actually, if you study programming languages and how they verify programming language systems, it's all about just describing what are the possibilities in the future. And this shows you the possibilities, and this is often called a non-deterministic representation of the world, as opposed to a probabilistic or stochastic. Right? So sometimes people equate these two things, non-deterministic and stochastic, but often non-deterministic is it just gives you the possibilities, and you're interested in problems like, is it possible to get someplace? You don't care about the probability. But in this class, for the most part, in fact, all the time, we're going to be talking about probabilistic systems, Markov decision processes, where you assign likelihoods of ending up in the possible locations. Okay? And typically, we're only going to draw arcs for the non-zero probabilities. And so you'll notice here that for a particular action coming out of a particular state, the probabilities have to sum to 1, right? And, well, why is that? Why do they have to sum to 1?
Because if you didn't, there would be some ephemeral non-action that could potentially happen.
Yeah, I mean, it's a hard question to answer because it's so obvious, but basically you have to end up somewhere, right, in the next state, and that may be where you already are, but these probabilities have to sum to 1. And so in this case here, you see A1, we're not even drawing the arc here and labeling it with 0 probability. We just draw this one arc that has a probability 1 there. And then we could put the rest of the arcs on there, and this gives you a complete description of the transition dynamics of an MDP, right? So now we could say, if we start out in S0, and I said, well, what happens if we executed action A0, 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 A1? We could actually, if we wanted to, figure out the probability of where we might end up after that sequence of actions, right? Using this probabilistic transition system. So this tells you how the system works, what your actions do, where you're going to end up. What's missing from this picture? Yeah, it doesn't tell us what we're trying to do, right? Do we want to be in S0 or do we want to be in S1? Or do we want to sort of transition between them somehow? So this only talks about the dynamics of the world, not the goal or the objective. And for Markov decision processes, usually the objective is going to be specified or parameterized in terms of a reward function. And there's lots of variants for how you specify a reward function. In this class, for the most part, we're going to specify it by saying each state action pair has a reward associated with it. Okay, so this says that if you're in state 1 and you take action 1, you're going to get a reward of 1. Okay, so there's lots of variants of this. The book uses a different one, and I'll talk about the relationships later on here. Sometimes the rewards are placed on states. Sometimes they're placed on state action next state pairs. Sometimes the rewards are stochastic. It turns out that all of these are mathematically equivalent. I'll have some of these homework assignments that show you that they're mathematically equivalent in the sense that if I give you an MDP like this, you could create an equivalent, in some sense, MDP that has rewards only on states, for example. You'd have to do some enhancement to the state space, but these are all equivalent in a mathematical sense. All right, so we're gonna spend some time later on talking about, well, now that we have these rewards and these transitions, well, what is the objective? I mean, intuitively, it's to take actions that are going to accumulate lots of reward over time, but you have to specify that more precisely. And we'll wait to do that in a little bit. But we're also going to want to be able to write down these MDPs mathematically. And so this is just showing you some of the notation that we'll typically use. So the transition probabilities, we're often going to use this notation. T is the transition function, and it takes a triple, S0, that's the source state, A0, that's the action you take, and S0, that's the destination. And this is the probability of, if you're in S0 and you take A0, what's the probability of ending up in S0? Okay? And you can see that it's 0.2 from this diagram up here. Right? So this is the conditional probability way of writing it. Often we just use this transition function notation. And I'm not going to go through all of these, but this just shows you, notice here we write down the 0 probability case. For the reward function, you'll typically just write it like this. So a reward is a function of the state and the action. And so in S0 and A0, we got a reward of 0, right? So this is just showing you the equivalent, how the graphical notation relates to the formal mathematical notation. So any questions about this notation? Yes?
The way we have formulated reward, won't it just support enforce rather taking a particular action rather than ending up at a particular state?
Well, you have to be in a particular state to take a particular action. So if there's a state where the action gives you a million reward, you have to get to that state somehow, and that may be the whole problem.
Yeah, exactly, but it does not incorporate the transition probability of ending up at a state. It just incorporates which state you're in and what action you're taking from that state.
Yeah. So as I said, all of these things are equivalent, and I'll actually have some homework problems where I'll say, okay, what if you define your reward function as a function of S, A, and S prime, the next state? You can always transform that MDP into another MDP that is just in terms of S and A, or just in terms of S. You have to increase the state space, but the MDPs are equivalent in the sense that you could solve any of these MDPs and the solution would be a solution for any of the others. All right. So any other questions about this? All right. So let's look at some examples. So I haven't really told you formally what the objective is for solving an MDP, but intuitively it's just to accumulate lots of reward. And so it's useful to be able to look at some of these diagrams and just say, well, what would be the optimal policy intuitively? Okay. So this is quite a bit to show you right off the bat. But let's take a few minutes just to look at this and then decide what we think would be the right thing to do in every state. So state 0, we have an action that will just keep us here, right? And if we said our action in state 0 is going to be A1, we're just going to get like a reward of 0 every time, kind of safe, but you're never going to get any positive reward if you just do that. So we have another option, which is this A0. It also gives us a reward of 0, but we have a chance of getting to one of these two states, right? We have a big chance of getting here, right? 99 times out of 100, you're going to end up over here in S1. And if we look at S1, what do you think about that? That's, if you take A0, you're going to get a negative reward. That doesn't seem very good. You might as well have stayed up here, right? You might as well have stayed here. Here you get negative rewards too. So S1 looks like a pretty bad place to be, right? Because you could have stayed here and just been safe and got 0 reward. But see, we have an option here. If we take A1 enough, right, we might end up down here. And is S2 looking like a good state to you? Yeah. Why does S2 look good? We can just kind of take A0 and just stay there forever collecting money, right? That's what. So S2 is really that's sort of the gold mine in this MDP, right? That's where you want to get to. So if all of this is just kind of work to get to the gold mine. And so what do you think the right thing to do is in S0? If I'm going to let you live forever? Who would like to take A1? Who thinks the right thing to do is to take A1? So A0 seems to be the winner. And so even though you're going to have to put up with this negative reward, right? You're probably going to end up in S1, and then what are we going to do? We're going to take A1, right? And then after we take A1 enough times, we'll end up here. 1 out of 10 times we'll end up there, and then we're happy, right? And so if you're going to live long enough, you might as well, pay this little price. Like this is like, you started out, you were born, and now you're in graduate school, and you're. It's not random. Well, it is kind of random when you get out too, right? So every year there's some probability you get out, and then here you get a job at Google or something, and you sell ads. So that's sort of life, right? So now that was a pretty obvious case, right? Because we had this money state. Now, what if we took away that money action and just looked at this MDP? Now, is it so clear what the right thing is to do? I don't know if this has an intuitive solution, and I don't think we've actually specified enough to know what the optimal solution would be here. But what's going to happen, right? You're going to want to try to come down here. or maybe not. But if you do try to come down here, you're going to get a reward, 8 times out of 10. But then you're going to have to start all over and go around this loop. You're going to get some negative reward. It's kind of hard to calculate. Like, if you do try to go around this loop, if you're going to end up with a positive expectation or a negative expectation, right? So our algorithms are actually going to tell us what the right thing is to do for problems like this when it's not very obvious. Okay, so some of these are obvious, some are not so obvious. All right, so I don't want to spend much time on this, but this is just, if somebody does say, what is an MDP to you, it's really this, it's a 4-tuple, right? There's just 4 things that specify an MDP. You have a state set, and for now we're just going to assume the state set is finite, has no internal structure. And you have an action set. We're going to assume there are M actions. And then you have to specify T, the transition probability. We've already talked about that, right? And one just to make sure we're understanding things. So if I wanted you just to write down all the parameters that are needed to specify T, right, the transition matrix, how many numbers or parameters are we going to have to specify? Okay, so I'm telling you there's going to be N states and M actions. Yes. Okay, so N times M minus 1. So, okay. So that's a tricky one, but he's right. So if we look at this, so for every state action pair, every start, state, and action, you've got to, there are N times M of those, right? So you have to specify something for every one of those. And for every one of those, you have to specify the probability of transitioning to each of the next N states. But those probabilities sum to 1, so you really only need to specify N minus 1 numbers. Right? It's a technicality. It doesn't really matter too much. But roughly speaking, it's Mn squared to write down all of the numbers for an MDP, a finite MDP, for the transition matrix. The reward function, that's pretty straightforward, right? So for every state action pair, we have to write down what the reward is. So it's going to be N times M numbers, right? And those are the only things you need to specify for an MDP. And so when you produce your algorithms, like one of the most basic input to an MDP solver will be these transition matrices and the reward function, and then your solver will spit out a solution. All right. We won't say too much about the reward function. There can be reward functions can specify all sorts of things. We'll be talking about that some. So what are the assumptions that go into Markov decision process? Like we're modeling the world somehow, and what are the assumptions about this model? Well, the first assumption is that it's time invariant, and well, I guess maybe that's not the first one I state here, but basically we're going to use this notation. St is the state we're in at time t. At is the action that you take at time t. And why is it called a Markov decision process? Well, it's because there's the assumption of the first order Markovian dynamics, which basically means that the only thing that influences where I'm going to end up next is my current state and the action I'm going to take. Right? That's what this says. This says that, well, if you consider what's the probability that at time t plus 1 I'm in state S, given the whole history, right? That's going to be equal to if I just know the last state and the current state and the current action, right? So this history doesn't matter in terms of defining the probability. And this is our intuitive model of physics. Like if you knew if you're in a basic physics setup, if you know the state of everything in the world, you kind of assume that kind of determines what the next thing is going to be, as opposed to there being history. And you'll have some problems where, some homework problems, written problems where, uh, so you can also have second order Markovian dynamics where the transition probability depends on the last two states, for example, or third order, the last three states. And it turns out that you can always transform a third order or nth order Markov system to a first order system by increasing the states. And you'll see that's something, you'll do that in a homework problem. And so that's another one of these equivalences. If you have a second order system, you can create a first order system and use your first order solver and get a solution for the second order system. So the first order assumption is not a big major assumption, but if your problem is second order or nth order, it does make the problem more complex. It's going to be larger in a sense. All right, so that's the first assumption. We're also assuming that the rewards are just going to be dependent on the current state and the current action, and that they're deterministic. So we're assuming deterministic rewards. We'll see in a moment that's not really a big deal. We can relax that if we want. We're also assuming stationary dynamics, which means if I'm here today, and I'm in a particular state, and then if tomorrow I come here and I'm in the same exact state, everything's exactly the same, the world is going to behave exactly the same. Right? So absolute time does not matter in terms of how the world works. That's typically how we think about things in intuitive physics as well, right? If I tip over a block tower today and then I do the same thing tomorrow, the same thing's going to happen. So and this is just how you write that down mathematically. And then we're also assuming full observability, and this is probably the biggest assumption that Markov decision processes make. Is assuming that you can observe the full state of the system. In the real world, we can rarely ever do that. In virtual worlds, you can do that to some degree. So there's a whole class of problems or models called partially observable Markov decision processes, and those sort of relax that assumption. But you can also reduce those to Markov decision processes in certain ways, and we'll be talking about this as we move ahead. But for now, we're just going to assume full observability, and we'll move ahead and show how we can relax that later on. So any questions about these assumptions? Right, they're not that exciting in terms of assumptions, but they're pretty crucial because these assumptions are actually what allow us to write all these equations and define these algorithms that we're going to define later on. It allows us to decompose the planning problem. All right, so if you're going to be reading the book, I do recommend you do this. You'll notice that the notation they use is different from what I use in these slides, and I actually think it's good for you to be able to go between notations, because when you start reading papers, people are going to use different notations all the time. Something that's very common is some people will use, instead of rewards, they use cost functions. And so then everything's kind of reversed. I'm trying to maximize reward or minimize cost. You just have to get used to working between these things and not caring too much. But I want to convince you that we're not losing anything by using our notation versus Sutton and Bartow's notation, even though their notation does seem to be more general in a sense. So we talked about how we're doing things. Their notation, they just specify a set of states. Their action is actually, this A is actually a function that takes a state and returns a set of actions. That's not that big of a deal, right? Most of the time in the book, they actually just assume it's, the set of actions is the same for all states. In practice, this is the interface that you're often going to have. Like you're going to have like OpenAI Gym, you're going to have a function that you can get the set of actions that are available in a state. So this is more what you'll see in practice. The biggest difference, the thing that looks like it's the biggest difference, and maybe our model is not general, is this: instead of specifying T and R, they specify one function, P, the transition function. And this basically says if you're in state S and you take action A, what's the probability of ending up in state S prime and getting reward R? Okay? And mathematically, they don't. I mean, it's not too rigorous of a book mathematically. They technically would have to discretize these rewards to make this make sense. Otherwise, you would have to have a density function. If that doesn't make sense, don't worry about it. But just assume there's a finite set of rewards. That's how their book sort of needs to work. And this seems like a very general way, right? So one way that this is more general than ours is the rewards are stochastic, right? And what's another way that these... Is there another way you can see that this seems more general than what we're specifying up here? It's kind of subtle.
That there's a function returning the set of available states that you can transition to given a certain state. So you could limit the number of states one can transition to, and you don't have to enumerate zero probabilities for states you can't go to.
To some degree, but you could say that we could make this T function have a similar sort of interface. It just returns like a set of states. What actually are, when we start implementing algorithms, we're going to be doing something very much like that. Because it is true, when you have thousands of states, having to enumerate over all the zero probabilities is a big waste of time. But one of the things here is that S prime and R could be highly correlated in complicated ways down here, but up here they're kind of independent, right? It feels like they're independent. And so it feels like this might be more general, but we're going to see that not really. So what we're going to see is that for most of the algorithms, and this is because most of the algorithms are going to be optimizing some form of expected reward, expected future reward, these differences won't matter. And so you can, we'll go through it here, but you can look at it also on your own. Well, let's say we want to convert Sutton and Bartow to our notation, right? So they give us this, right? So this is like I've got an MDP solver for my problem, for our representation, but I want to solve problems from Sutton and Bartow where they give me this P function, right? So how would I do that? Well, I've got to transform their P function to R and T. And so one thing you can do is we're going to say that the reward, our reward function, is just the expected reward that you're going to get for being in state S and taking action A, right? That's what these summations are doing. This is the expected reward. So we're kind of we're taking their function and we're just averaging, and what's the expected reward? The other thing we'll do is we're going to get our T function by marginalizing out the reward from this function. Just getting rid of it by summing it out. And so that's done like this. Okay, this is a basic rule of probability. And so these are things that you could do, right? You could do that. And then, so we take their P function and we get R and T. Then we could run our algorithms. And what I'm claiming, I can't really prove anything to you now because we haven't defined objectives or algorithms. But basically, if you run any of our algorithms and any of their algorithms for the P function, or you run them for this transformed R and T, you're going to get the same results. They'll be mathematically equivalent. And this works out because our objectives are typically going to be trying to optimize expected reward. And so in some sense, we're just building the expectations into T and R here, whereas they don't, they sort of make it explicit. This should not be clear to you yet, but once we learn some algorithms, you'll see that this is equivalent. Okay, and so one of the interesting aspects of this is that it's kind of unintuitive. A stochastic reward function, it doesn't fundamentally change things. Like if you have a stochastic reward function, you can just work with the expected reward function, and the algorithms are going to give you the same answers. That's kind of an interesting aspect of all this. And then we can convert from R notation to Sutton and Bartos with no problem because they're kind of more general, strictly more general. All right, so maybe with the time this might not take the whole time, but I wanted to, one thing that you want to get good at is thinking about problems and then how do they map to the MDP formalism. Like, okay, here's a problem. What are the states going to be? What are the actions going to be? And sometimes this is an iterative process. Like the first time you come up with something, you'll find some bugs, and then you have to modify it. Probably most of you are familiar with Tetris. I mean, you have who's familiar with Tetris, right? Yeah, it's hard to tell. I mean, when I was a kid, there weren't nearly as many games. Now there's all kinds of other distractions. But just in case you're not familiar, I found a Tetris game, right? So it even has sound effects. And I wish so you can move this thing back and forth, and I don't know what this does. Oh, okay. So you can turn the shapes around, right? Like this. Then you can push it down. I'm not doing very well. But we're just trying to see what this game's doing. One thing to notice is that there's a shape here that shows up, right? And that's kind of a random assignment, as far as we know. It's not adversarial or anything. And so you keep on doing this, and I'd like to do one reasonable thing here. We'll see if we can. I don't know. What do you think? Do that. Uh-oh. There we go. There we go. So I just want to make a line disappear. There we go. Okay, so that's the big reward, I guess. So anyway, this is Tetris, and back to the slides. We'll see that I've got a picture here of Tetris. And Tetris happens to be it used to be a popular benchmark for reinforcement learning. Basically, you can train a reinforcement learning agent to play Tetris forever, more or less, if you do it right. And we'd like to just go through the exercise of trying to figure out, well, how would we represent Tetris as an MDP? So what would you say should be the action space? That might have been fairly apparent.
Moving a block left or right, or flipping it are the main ones.
Yeah, so you can move it left or right. I can. So the action space would be something like left, right, rotate like that, and then you can make it go down, but that's just kind of a speed up, right? It's not that big of a issue. So we could say there are 3 actions, right? That seems good enough.
Wouldn't it be pertinent to define leaving it, like you say, moving it down, but that's also leaving it in its stationary position to the next step?
Oh yeah, so I guess we should have a no-op too, right? So if we're thinking of these actions can be done at every discrete step, you kind of want to have a no-op, right? Otherwise you're going to have to, it would be really hard, right? You'd have to time it exactly. You'd have to move left, right, left, right, left, right, and rotate it just right. So we'll have a no-op as well. All right, so we got those four actions, and yeah, we'll ignore that expediation action that just sends it to the bottom. This is one action space, and we'll talk a little bit about, there are some other choices as well, but we'll talk about that in a little bit. So how about the state space? This is a little trickier. right? So how should we start thinking about like it's usually when you're trying to figure these things out, it's useful to think about, well, what if I was writing a simulator for Tetris, right? What would be the data structure I need to actually keep track of the state of Tetris and update it every step? And that's exactly what you need to do to specify an MDP. So how about the state space? Like, what components does it have?
Probably you want something to represent which boxes are filled of like the bottom half.
Okay.
You want it that intersected right with what piece you have and how it's oriented.
So one thing you said, so we'll think about the state space. It's going to be a cross product of something, right? So we could, I don't know if this is going to work, but you could have this matrix that has, these are sort of all the cells that are available to be filled. And let's just say for now that you're just going to have a 1 in places that have something, okay, like that. Right? And so you could say one part of the state space will be a binary matrix that tells you what's occupied and what's not. And while we're at it, why don't we just throw in, we could have 1s for the thing that's falling down, right? That may or may not work. Right? So there could be some problems with that. But let's work with this for a bit. So any cell that has that's not empty, we're going to put a 1, and that's our basic state space. And then also we have the next, like that's part of the state too, right? The next piece. So the next, that would be part of the state space. We could just have a discrete number of those things, and this just is a discrete variable. So how do we know if this is an adequate state space? We have to be able to define the transition function and the reward function in terms of that state and action space. And so how would we define the transition function, right? So we have to say how this changes for each of these actions. So, I don't know, how about no-op? Let's work with no-op first, right? So we have, and I'm not going to write this out too carefully, but so no-op, and then we've got next states. So how would we define the transition function for a no-op action? Any ideas?
The falling piece moves down 1 spot in the grid.
Okay. Now one thing that you mentioned is the falling piece, right? So could there be some situations where we have a hard time from this matrix determining what the falling piece is?
If it's going down, it's like that.
Yeah, I mean, it could be I mean, you can have all sorts of crazy pictures in this game, right?
Slide is a good example.
Right. So, yeah, the slide, yeah, it might be, but here it's pretty unambiguous what the falling piece is, right? So we would know that the ones up here have to be falling because you can't have something just levitating, I guess. But there could be a situation, I guess, if that were to go down a little more. Yeah. So if that were to go down like this, it's hard to know what the falling piece is in this picture here, right? It's kind of it's ambiguous, and so this could be the falling piece for all we know, this little place. And so the problem is that we've seen that our state is not rich enough for us to define the dynamics unambiguously, and so we have to enrich our state representation, right? So what's the obvious solution?
Give individual.
What's that?
using another matrix just for performance.
Yeah. So we could have another matrix, or another thing we could do is we could just have a different symbol. We could put like a value of 2 for the falling piece or something like that. And that would tell us, that would let us disambiguate what the falling piece is versus the filled-in cells, right? And these are all very common. Like when you start defining MDPs, you'll run into little bugs like that as you go, and you just fix them as you go. So now no-op should be pretty easy. I mean, you'd have to write code to implement the function, but is it going to be a deterministic transition, or stochastic, or a mix of both? Yep.
I believe, is the next piece randomly determined? I believe it is.
Yeah, we'll assume the next piece is randomly determined.
Okay, then. Stochastic.
Right. But for some steps, it'll be deterministic, right? And so the transition function basically would have to say, okay, is this about ready to, did this land someplace, right? And if it landed someplace, then what's the next state going to be? It's going to turn these into 1s, right? And then this next thing is going to appear at the top, and then we're going to have a random entry here, right? If it doesn't land, then it's deterministic. It just would go down. Okay, so it's something you could code. It would be a pain, but it seems like this is a rich enough state representation, I think, unless somebody else finds a bug. I mean, sometimes there might be another bug here, right? And you could do this for all of the actions. We don't want to go through all of the details, but the main point is that would probably be enough to represent Tetris. The reward function, that might just correspond to the score, right? And that would be very easy to encode using this state representation. You'd have to. There's a whole lot of dynamics that we haven't talked about, like lines disappear, but those are all things that are well defined that we could do. All right, so I think that's it for today. So the next lecture, we're actually going to start talking about, well, what are the objectives of solving an MDP? What are some of the problems? And we'll actually get into some algorithms for solving them. All right, so I'll see you on Friday.